This week we will start by actually going back to day 1, where we started studying Maxwell's theory, and all of a sudden we decided to stop and switch gears. So today is time to go back to it. In one of the tutorials, you were asked to compute the field equations. Well, actually, you were asked to find the Lagrangian that would give rise to these field equations, which are Maxwell's equations. Okay. As we discussed, the other set of equations that people usually write down are actually an identity. Once you write the field strength F mu nu as what is called the exterior derivative of the gauge potential. That's what this is. So the field equations are this. Now in terms of the gauge potential, they are given by this. Now it might be convenient to write this in such a way that we can pull out a factor of A always, okay, of the same component. So one trick to do that is to write this A nu as, say, nu rho, A rho, and we can write this guy, this A mu, as eta mu rho, A rho. And therefore, the equations become the following operator. Acting on the same object. Okay. Now, if you remember, this is the object that people like to call the box operator. So we have eta nu rho, the box operator, minus this combination here, which with this index, I can happily move this guy up, and we have something that looks like this. Okay, so these equations make it clear, so it's obvious from these equations, that if you take your gauge potential, which is a solution of these equations, and you shift it by something that looks like this, okay, then you get another solution of the same equations, okay? In fact, everything from the beginning is invariant. The field strength is invariant under this transformation, and this is what is called a gauge transformation. Okay. Yes.
If I'm not mistaken, we considered last time an extra term on the Lagrangian for Maxwell's theory, right?
No, you didn't.
I mean,
You mean there was another term? Yes, but you were also asking the tutorial to find out that such a thing. Well, first of all, you got something else which depended on a parameter, right? As your attempt to finding a Lagrangian that gives rise to these equations. So the extra term that you wrote down there, right, was something that didn't affect the field equations. Were you guys able to write the extra term in terms of f? Was anybody able to do it? There was an extra term, so you're right. So there was an extra term that had a constant, that depending on a constant c that we couldn't fix by requiring that this Lagrangian would give rise to something like this. So you found what this was in terms of A, but it turns out that you can actually write it in terms of f, and it's something that looks like this. So terms that you can add that have this form, which do not affect the field equations, are called topological. And they play a role when you have to consider configurations for the field that have some interesting properties that we will not get to discuss in this course, okay? But at some point you will, especially when you consider non-abelian gauge theories, when you consider particles of helicity plus minus 1 with several species that can interact, okay? And we know very well now that they interact through coupling constants that satisfy Jacobi's identities, and they give a very rich theory that connects Lie groups to manifolds, and this thing is going to be very important then, but not for us. Okay. Very good. So,
in those cases, can you fix the C?
Well, actually, in the non-abelian case, when we actually have QCD, I mean, we know that the description of the strong interactions is based on a theory that has as interaction terms structure constants of a Lie algebra of SU3. In that case, there is a term like this that you can write down, and we know that it should be there, changing the physics, because there are, as I said, effects that are not coming from perturbation theory. There are effects that are of a different sort, and that C should be something that affects the physics. Now people go and measure it, and then they find that that number C is extremely tiny, very, very, very small. And nobody understands why. Yes?
So I think there's an upper limit on it, right? So we don't really know if it's 0 normally.
Yes, that's right. So there is it's only an upper limit, there is none. But that upper limit is very, very, very small. And nobody knows the mechanism that tells you why that number has to be very small. There is a proposal by postulating a particle called an axion, but the axion hasn't been seen, so still a proposal, okay? So the problem of why that number is so small in QCD is called the CP problem, the strong CP problem. Okay, very good. Now, the fact that we have this redundancy in the description, because in fact it's a redundancy, anything that we actually measure is the electric field and the magnetic field, and their values come from the components of F. So nothing changes when we perform this transformation. Therefore, you can ask, well, is this a problem? Well, in the classical theory, it's not a problem, because what do? Well, that's something that you did many times. You choose a gauge fixing condition. Okay, you impose a gauge fixing condition, and then you hope that the gauge fixing condition is respected by the dynamics so that it can stay there at any given times if you impose it as an initial condition of your field configurations. So 1 is the Lorentz condition, which has kind of a historical accident. It has the T. So the condition that one can impose is to ask the gauge potential to have 0 divergence in 4 dimensions, okay? So would this fix the gauge completely? Meaning, would that fix the redundancy? No, it doesn't fix it. Well, but first of all, we have to check that this is a condition that we can impose using our redundancy, okay? So let's actually check that. So let's check that this is achievable, okay? So if you have any gauge potential, A mu, okay, let's call it A mu prime, we want to see whether in this space of all possible A's that I can get out of A prime by adding something of this form, I can come out with one that satisfies this. So now, if you have, for any A, okay, the space of all connections such that A is equal to A prime plus this derivative, okay, is called the gauge orbit of A prime. Okay, so we want to know whether there is somebody in the gauge orbit of A prime such that this condition is satisfied. Okay, if that's always possible, then we're in business.
Why? So we can't formulate the field theory properly without fixing the, without the gauge condition. Can we just not have that freedom working without?
Can we try and describe this without having this freedom? Is that the question?
No, so you're trying to fix the mu, right?
I'm trying to fix a redundancy in my description by saying, well, given that any of these guys will do this, will give me the same physics, yeah, I'll try to make a choice. Okay?
So what my question is, can you not formulate everything without making that choice? Why do you want to make the choice? Why is it important to make it?
Well, it's as simple as saying, well, if you start with an initial boundary condition, right, for your differential equation, right, and now you try to evolve it, basically the evolution doesn't have to keep you in the same, it doesn't have to give you a unique solution, right? That is a statement that this operator as a differential operator, okay? Imagine the space of functions as a vector space, and the differential operator being some sort of metrics acting on this. So the statement that we want to make, or the statement that is true, is that this as a differential operator is not invertible. Okay? So if on this side you put a conserved current, then this operator is not invertible, and you cannot find a unique solution. Okay? So it's just that your system of equations will not be well defined. So you have to fix your gauge, and after you fix your gauge on those gauge orbits, then you can think that your differential operator is fine, and then solve the evolution. Okay? Very good. So then what do? We just say, well, imagine that the choice I made of A prime gave me some function of x. Okay? So you do this. So fine, the choice I made, the original choice I made, failed to satisfy that condition. But then I say, well, let me choose another one. Let me write A prime as something, okay, minus some function of minus a gauge choice, okay, something that is in the same gauge orbit as A prime. I just put it in here, and then what I get is something that looks like this. Okay. But now we can choose our function w of x such that this is true. And this system of equations this equation always has solutions, and therefore we can plug it back here and find a representative in the gauge orbit that satisfies the condition. Okay? So this is a good condition. Now, is this a complete gauge fixing of the problem? Well, it's the Lorentz gauge is not a complete gauge fixing because precisely if we choose a function whose box is 0, then the gauge fixing is blind to it, okay? So we can still impose after gauge fixing, gauge fixing, we can still take a representative of the gauge orbit and shift it by some special functions that satisfy this condition, okay? So we will see if we can go ahead and do this. Now, you would say, why not choose a different gauge, something that completely picks a single representative from your gauge orbit and doesn't leave you with this smaller space, but still some infinite dimensional space? Well, the reason is that there isn't any other gauge choice that is known which will allow us to do all the calculations in a manifestly Lorentz invariant way, okay? So Lorentz invariance keeping manifest Lorentz invariant implies is that we have to deal with this little extra redundancy. Okay. Yes.
Can you repeat again why this is going to complete gauge fixing? So we can find a function omega so that the four divergence A is 0.
That's right.
And then where's the other freedom coming from?
Yes, you say, well, now imagine in the gauge orbit of A prime, right? That I found a representative that satisfies the Lorentz condition. But if I add to that representative, say this is your magic representative, and you add to that this guy, where this guy satisfies this condition, you still satisfy the Lorentz gauge. So the Lorentz gauge still leaves as a small gauge orbit inside. Yes.
You say that we have to deal with this gauge because it's manifestly Lorentz invariant.
Yes.
Is this the only gauge fixing that is Lorentz invariant?
Well, that's what I said before. This is the only one that I know that is manifestly Lorentz invariant. And which is reasonably simple. I mean, of course, you can come out with functions of that, right?
So what do you mean by manifestly? Like it's obvious in the sense that it's Lorentz?
Yeah, so let's pick another choice. Say the Coulomb gauge. You set A0, the 0th component, to be 0. So you're picking the time component. You're doing something drastic. Okay, so very good. So we have this. Now, so how can we modify our theory? In such a way that we can proceed with a quantization procedure, okay? We know that when we try to do it during day 1 with that Lagrangian, we face a problem. What was the problem we had? Yeah, pi 0 was 0, right? So let's try to come out with a theory which is not Maxwell's theory and see if we can do something with it, okay? I mean, it's not Maxwell's theory, but we hope it's close to Maxwell's theory. Okay, so we're going to have this, and we're going to add to it a term of this form. Okay, it's clearly not Maxwell's theory.
So this is hard.
So in general, we could have added something else here, something like this. Okay. Now, when lambda is equal to 1, people call this the Feynman gauge, or the Feynman choice, right? So we can put something like this. So this is a new theory. Okay. Classically, if we start with this theory, okay, and we find the field equations. And on top of that, we impose a constraint. That we are on the Lorentz gauge, then our not Maxwell's theory plus a constraint becomes Maxwell's theory, okay? So not Maxwell plus a constraint equals Maxwell. Looks silly now, but you will see that it's important.
So just adding 0 is like...
Well, not to the Lagrangian, right?
No, but you set the condition d mu is 0.
Yeah.
You work it out.
After we find the field equations and we study the dynamics, we impose this constraint, yes.
So on the right-hand side, is that Maxwell's theory in the Lorentz gauge? Is that what you get?
There is no such thing as in something, right? It's a gauge. So there is only one Maxwell theory, right?
Right. So on the
If my
left-hand side,
observables depend, if my theory depends on the choice I made, then I'm in deep trouble, right? So of course, maybe I'm going to do something wrong, and my observables will depend on that, right? But this, if I had started with another gauge fixing, okay, I should put it here and impose that particular constraint, and I'll end up with the same Maxwell theory, hopefully. Do you agree with the statement now? I mean, this could be any gauge choice, any gauge fixing condition, f of a. Now you can replace it and put it here. And you wouldn't say that you got Maxwell's theory in that gauge. You would say you just got Maxwell's theory.
lambda is a Lagrange multiplier.
You could think about lambda as a Lagrange multiplier, and in the next course, you will find lambda as a Lagrange multiplier. Yes.
With respect to this, I mean, it's a Lagrange multiplier, but is there a particular reason why this quadratic in
Because we want to...
Yeah, because in the variation, you want to get it back.
Okay.
We want to recover Maxwell.
You want to get the variations.
So, this is apparently part of that term, the topological.
No, it was a piece of it. Yeah, but there was more. So this is not topological.
Yeah. So why couldn't we just like use the entire topological term and use?
Because we know the topological term doesn't do anything to our field equations. We will get exactly this. Now we're going to do it with that, right? So let's study the field equations of our not Maxwell theory. Okay. So what are the field equations? So again, we do our standard variations. So when we do the variations of the first term, we get back the term that you got in the first tutorial, right? Now, when you do the variation of the second term, you're going to get something that looks like, what is it going to look like? It's going to look like eta. Yeah, so we could calculate it. Let me actually write it in the form that we have over there, because it's going to be more useful. So if we have the field equations in this form, okay, so these are the pieces that came from the original Lagrangian. Then the piece that we're going to get from the new Lagrangian actually happens to be, and that's why the lambda equals to 1 is a nice choice. Guess what's going to happen? We're going to get something that looks like plus. This is coming from the new term. Okay? So the job of the new term, precisely if we choose lambda to be 1, is to cancel this term. And this implies that we get as equations, just this with this, which is the same as 8 nu equals to 0 for nu 0, 1, 2, and 3. And that looks just spectacular, right? I mean, isn't this an equation that we know how to solve very well? Well, maybe you don't recognize it, but let's make it more complicated so that you recognize it. Now you recognize it, right? That was easy. Yeah, this was, but this one is even easier. Yeah, so all it happens, and remember, when we studied the scalar field, we said that this scalar field, we could have several components, right? It could be many scalar fields. So we have this equation.
But there's no m squared.
Exactly. So there is no m squared. So all we have to do is everywhere we were dealing with our equations for a scalar field, we just set m equals to 0, and we set this index I to be the index nu.
So in that case, you have scalar fields, so obviously they do not depend upon.
You have 4 equations right there, right? For each component of a nu.
Yeah, but is it equivalent to that entirely? Like a nu, so that's a vector field.
Yes.
And that's a scalar field. So what's the there has to be some, is there a fundamental difference? There is a fundamental difference.
There is a fundamental difference in the way they transform under Lorentz transformations. That's true. But as far as equations are concerned, and we're going to solve them, right? This is a differential operator in x, right? In time and in space, acting on 4 functions of time and space. And we just happen to have solved this equation. Right? Well, why not use what we know?
So
Okay.
those i's, we could just have them run from 1 to 0 to 3, and then it would be exactly the same situation.
Yeah, the i's go from 0 to 4, 0 to 3, yes. Yes.
We have this constraint that del mu and mu equals 0 that we haven't put in yet, right?
Yeah, that's why we're not doing Maxwell's theory yet.
I mean, that constraint creates a dependence between the different components of a mu, right? So it's equivalent to solve this differential equation, treating them independently, and then put in that constraint. It's equivalent to putting in the constraint and then solving the equation.
Yeah, exactly. Yes, classically, yes. Yes, because this is a constraint that is preserved. This is an exercise. It's a constraint that is preserved by the dynamics. Okay. Now, we want to keep this. Maybe. Yes.
Isn't that like that when goes to 0? And a little bit problematic with the propagator?
No.
No, not at all.
No. As Ibra pointed out, the propagator is not infrared divergent. It was a very important contribution.
So what did I point out?
You pointed out last week that the propagator has no infrared divergences when m is equal to 0.
And one of the things, remember when we calculated this 2-point function outside of the light cone? Your correlated function was e to the minus n r over r, right?
Yes.
So if I said m equals to 0, this assumption of causality that you impose for your scalar field is false.
No, well, the cancellation with the cancellation didn't depend on m, right? Outside of the light cone, the cancellation didn't depend on m. Very good. So what's the solution? So let's write the solution. That's the solution, right? For each component, we have exactly the same solution that we had for a Klein-Gordon field. We have 4 Klein-Gordon fields. We just solve for each one of them, and we call the momentum components of each one of them by the index that they have. Right? So far, so good. Now let's do the quantization of this. Yes?
Why we're restricting our A to be real at this point? They could hence write it at 8 star.
Oh yes, of course. A is a real field. Just like our Klein-Gordon field was a real field, A is a real field.
That's a choice, I guess.
No, the gauge potential that you learned is a real field. I mean, it is a choice, but I mean, it's just a standard. It's just a standard. Well, it's a standard point of view that what we're dealing with that describes the electromagnetic field is a real vector field. Okay. We could try to generalize it and see what theory you get. Okay.
Does it have any interesting consequences?
Well, we should try to think about it. In fact, so when we go to the non-abelian case, when we have more, then one could try to see. In fact, so making it complex in a sense is, as you know very well, because you all did your homework, right? And you submitted your homework. Nobody's left behind.
A couple have.
Okay. So you know that we can think about them, complex fields, as collections of real fields. Okay? So we will have a collection. And we will have to see if that collection simply becomes a collection of free vector fields or if they can interact. By now, we know that if you have only 2 copies, right, can they interact or not? No? We already know that they cannot interact because they have to interact through the structured constants of a Lie algebra. And the smallest one we know has 3. Okay? So let's attempt to quantize our not Maxwell theory. Not Maxwell, but close. Okay, because otherwise there will be an infinite number of non-Maxwell theories. So what was the problem we had? We had precisely a problem with pi 0, okay? Which was this quantity. But now, it's not 0, but it's exactly this, okay? That wasn't meant to be a joke. So this is new. And this is new. Okay? Very good. So we have our guys. So having the momenta, we can just do canonical quantization, right? So if we want to do canonical quantization, we start by imposing equal time commutation relations. We promote our fields to quantum operators. This is 0, and the same thing for these guys. Oh, sorry. It's already done. Okay. Now comes the interesting part. You say, well, say we have a space-like component AI and a space-like component, these guys. Well, the commutation relation has to be the standard one, right? Okay, very good. But now we also have the zeroth component. So if we want the zeroth component to be part of this system, and at the same time make sure that we have Lorentz invariance, okay, this object must be Lorentz covariant. You know the difference between covariance and invariance? So something that is invariant is something that transforms as a scalar under whatever transformation group you have, right? Something that is covariant is something that is allowed to transform in any representation. It doesn't necessarily have to be a scalar, okay? In any representation of that group, okay?
So that's just to say it could be a vector or a tensor or whatever.
Yes, but there are many things that are not tensors, vectors, or anything. So imposing that is covariant is a very strong constraint.
But weaker than invariant.
Sorry, but weaker. Yes, but weaker because, yeah. In fact, something that is invariant is also covariant if you think about the representation as being the trivial representation. Okay. So we want this object clearly. This object cannot be invariant. So we have to impose this guy. We have to impose that this guy is covariant. Okay. So the way to make it covariant is to actually deal with the full vector index.
So why is this not invariant? This is not
Well, because as you pointed out, these indices are not random indices. These are space indices of a vector. So under Lorentz transformation, they transform, okay? But we only have 3 components, and we want Lorentz. So we need the 4 components to have even a chance of getting something that is covariant, okay? But then this is almost something nice, right? Because we know that this is minus eta ij, right? Remember that our signature is +1, -1, -1, -1. So this object is minus eta ij, and that means that the natural completion of this to make something that is covariant, that transforms as a 2 tensor under the Lorentz group, is to put minus, well, actually, sorry, yes, minus eta mu nu delta 3. Yes.
So are we putting this? Are we enforcing this, or would this follow if we worked out, say, the Poisson brackets between mu and pi mu? Would we get this up to a 9?
Yes. So you could also work out the Poisson brackets and get this,
Okay.
but using 10 more minutes. Yes.
Okay, but it's not something you're putting in by hand.
Yeah, it's not something that I'm putting in by hand. Right. So you can derive this from Poisson brackets. Okay. Very good. So everything looks great. Okay. Yes.
So the 3-dimensional delta function that would not be invariant to the Lorentz transformation. So
Well,
I could put in a factor.
The point is that we are evaluating everything at the same time on the left-hand side, right? Okay. But in any case, so as has been already pointed out, we can derive this from Poisson brackets, okay?
But last time, did we postulate the relationship between the commutation relationship?
Well, the postulate really tells you that you should compute the Poisson brackets on the classical theory and then postulate that they turn into commutation relations for the operators.
You have the overall sign.
Which overall sign?
I mean, if I take the 0, 0 component, that'll give me a minus side delta, right?
That looks like a small problem, right? And yes, it's going to be a problem. Okay. So now, let's pretend that Andres didn't mention anything. And we just keep going. Okay? So that's reasonable. So we just keep going. Okay? So if we just keep going, now we can promote our field to be an operator by simply asking this to be the adjoint operator to this one, because of course we want this to be a real field. As we have discussed, this is something we're imposing. We're starting with a real field, so this guy has to be the adjoint of this one. Now, as you did for the Klein-Gordon field, if we use this, the equal time commutation relations would imply commutation relations for our creation and annihilation operators. And they will be of the form minus eta mu nu delta 3 k minus k prime. Okay? Once again, we define a vacuum. We assume the existence of a Hilbert space, and we define a state, which is called the vacuum. And we say that the vacuum is defined so that no matter which guy acts on it, annihilation operator on this guy, we get 0. Okay? That all looks very good. And we say that particles or states are given by sequences of these guys. These are our states. Okay? So far, so good. No problem. Well, but there is a problem. Okay? Take any state.
So that is the full vacuum.
This is the vacuum of our theory, yes. This is a free theory. Yeah.
Okay.
We haven't even bothered to worry how this interacts. We're just trying to find a quantum theory for a free, yeah, I know, it's a, for a free vector field, okay? But there is a problem, and the problem is that if you take any state, okay? Well, the first thing that you see from here is that if the creation operators have a space-like components, they have the standard commutation relations that we are happy with, okay? So that looks pretty good. The problem will come when we have the zeroth component. Because then you have the minus sign that Andres was worried about, okay? So if you have this minus sign, something weird might happen. Well, let's see what could happen. So create a state by using your creation operator. Okay, let's call this K. Create another one, K prime, using the same creation operator. Okay, but different momentum, K prime. Now compute the norm of these two. Let's see, where do we do that? We can do it here. Now, if you compute the norm, what did you get? Well, you get 0. This one is K, and we have dagger K prime, 0, I believe. Now we use the commutation relation that we have over there, and we get minus delta 3 K minus K prime. Sorry, here. Is that okay now?
So you should have zeros on this expression as well.
Yes, sorry.
And is there nothing in our states to indicate this was created using the A0 component? Should we also have 0 for that? Just asking because I don't. Is there a way to distinguish between this created using A0 and this created using A1?
Yes, let's put a hat. Actually, it should. Let's say that we put a hat on any state that is created with an odd number of these guys, okay, of zeroth components.
Odd number of these guys.
So your exercise is to show that any state created with an odd number of these guys would actually suffer from this problem, okay? And what is the problem? Well, the problem is that you see, this is a distribution, right, that has support when k is equal to k prime. But at that point, this is supposed to be the norm of this object, okay? And we're getting a negative norm. So that is a very sick property of our Hilbert space. Yes?
A little bit confused when you have these different indices, mu and nu. Does that imply that I have 4 different particles that I can create?
You have 4 different scalar fields.
Yeah, so that implies that there are 4 different particles that I can create.
Yes, you can create 4 different objects, yes. And we're going to discuss that in a second. But let's try to get rid of this problem first, yes?
Could you solve this by just raising the index on a dagger?
By just... Well, if I raise the index on a dagger, remember this is the adjoint operator, so it would also be raised here, and it won't fix any problems. Yes?
Could we just call a dagger A and a dagger? And
No. Well, you could, but it doesn't change anything. Yes? Yes?
No, but you could call it
A dagger, and you can redefine the vacuum to be such that it's annihilated by the electrons.
Yeah, just think a little bit about it, and you will see that there is no solution of this by just relabeling things. Okay? Basically, because everything was fixed from these canonical commutation relations. Okay? Okay. So, but does this mean that Maxwell theory is wrong, or it cannot be quantized? Exactly. This is not Maxwell theory, right? So we were quantizing not Maxwell theory, but close to it, right? So it was very good that we were not quantizing Maxwell, because this would be a problem. Okay, no problem. Since this is not Maxwell. Okay, we still have to impose the analog of the constraint to make it Maxwell theory, right? Now, there are several choices. The first one is just to impose this as an operator statement, right? We just say, well, let's impose the constraint just as an operator and ask this operator to be 0. Would that be a reasonable choice? Looks like, but look at the blackboard. Would there be something funny happening?
Don't you go back to the same problem we had at the start?
Yeah, so we will be requiring that the canonical momentum conjugate to A0, pi 0, is identically 0. And why would that be a problem?
Because it would take you back to square one.
Yes, but why couldn't we proceed? So the answer is here on this blackboard, right? If pi 0 is equal to 0, then we will be in trouble.
If pi 0 is 0?
Yes, because then the 0, 0 should give us a non-trivial commutation relation, but we're going to get that we're imposing that this is 0. So this equation will be inconsistent. Okay? So option 1 So the first option, which is to impose this as an operator equation, is inconsistent with the commutation relations. Well, the next option.
Can you not modify your commutation relations a bit to somehow accommodate with that?
There is no way that we know how to modify the commutation relations. Remember, they came from the canonical way of doing it. So the second option is to say, well, this is not true as an operator equation, but it's something that imposes constraints on the Hilbert space. Okay? Maybe we can project the Hilbert space. Okay? Well, by the way, the notation that I'm using here now is not the standard. I mean, it looks very, very natural. I don't know why people don't do it like this. Very soon, we will switch to the other notation. But the reason we're doing it like this is that if you take the string theory course, then you will basically go through a lecture that is identical to this. So that's why we're keeping the muse and the news. Okay? And there, too, you have to project the Hilbert space. Okay? And this is something that is done many, many times. So how do we project the Hilbert space? Well, we declare that some states in your full Hilbert space are not physical. Okay? Yeah, it looks very convenient, right? You say, well, everything that has an H0 maybe it's not physical. So how do we do that? Well, usually the way to do it is by imposing a constraint. So you impose that an operator acts on the physical states, some physical state. So if the state is physical, okay, so you say if psi is physical, then this must be true. If it's not true,
is there a precise meaning of what physical means in this context?
Physical means that has physical meaning. And it can be used as a state in your theory to describe nature. Okay? Literally, that's what it means, right? Okay. We could try this.
So I don't understand. So A, what do you mean by projecting the Hilbert space? And B, how is this like, so effectively, if you set d nu and nu equal to 0.
Well, imagine that I have a two-dimensional Hilbert space, right? And then I design a projection operator, okay? The projection operator basically projects everything that has components on the second. You have a vector, right, that has two components. And I imagine the operator 1, 0, 0, 0. And I act with that object on all my vectors in my vector space. And I say, I'm only going to keep those that vanish under that. What are those guys going to be? The ones that only have a non-zero component in the bottom part, right? The other ones will be projected out. So it's a very non-democratic way of proceeding. You declare that those guys will be projected out. Of course, you have to check the consistency of what you're doing later, right? So here, the natural thing to try is to impose this projection operator. In other words, impose that annihilating a state with this gives you 0 if the state is something that you want to keep as a physical object, right? Okay, would this work?
So is this an if and only if or just if?
Sorry?
Is this an if and only if or just if? Are there physical states? Are there states which satisfy this but are not physical in addition?
Yeah, this is a definition of the
It is if
physical
and
state.
only if. Okay.
Yes. Okay. So, would this work? Would this be reasonable? Well, after all we have said, I mean, we spent 10 minutes on it. It better be. But the answer is no. Nope. Yes.
No.
You were going to say no, right? I know. Thank you. So Tibra was going to point out that no, this is not a good answer. Okay? But he's cheating because he's been in courses like this before. You should let everybody else to participate. Why do you think this is not reasonable? Well, one way to see that it's not reasonable is that you could split it into the positive frequency part and the negative frequency part there, right? And then say, well, okay, fine, so let me split it. You remember this definition for the scalar field? Yes. Okay. Now, this guy, I'm going to be in trouble. Yeah, so this guy is the one that has annihilation operators, right?
This was the plus was with the.
Okay, what we use in the past is irrelevant. So I'm just going to see what's my convention. Okay, I'm going to use plus to mean annihilation operators. Okay, and this guy to have creation operators. Okay? Well, now we can start with our object and ask, well, is our vacuum a physical state? I mean, it would be nice if the vacuum was a physical state, right? Well, let's apply this condition to the vacuum, right? What do we find? Well, yes, that's right. If we apply this condition to the vacuum, we find this annihilates this guy, but this guy will not give us a sensible object, okay? So the vacuum will not be physical. That's a little bit of an inconvenience. Sometimes it happens. In a string theory, there will be some theories where you would find that actually the vacuum has to be projected out. But not for us here.
So just the d mu acts on the a mu side, or the d mu is acting on a mu and that as an object.
The operator is continuing. That's the operator.
D mu and a mu is zero.
Yeah, and it's defined by acting with the derivative on that operator over there. The x dependence is only in the exponentials, right? Okay. So what would be a sensible choice to make? That's right. So the third choice is just to use the plus part. Okay. Now, doing this carefully and carrying out the whole quantization procedure, imposing this constraint on your vectors, on your Hilbert space, is called the Gupta-Weber quantization. Okay, and here is one of these quotation mark exercises, which is to read chapter 3.2 of Itzigson and Zuber, or section 6 of David Tong's lecture notes, to see how the whole procedure is done, okay? The reason we're not going to do it is that for the kind of applications we're going to have in the remaining many lectures of this course, we can get away by doing something much, much simpler. So we can get away I think this is called for all practical purposes, in this course, all we're going to do is to assume that physical states do not have A0 daggers in them. Okay. Well, look at the.
So doesn't it lead to problems when you just like get rid of the? So you're getting rid of the other part of your A, of your field. So if the third condition which you're imposing.
Well, yeah, we're going to see that we will have to do things a little bit by hand, okay, in this course. But in the next course, in Quantum Field Theory 2, you will develop a whole machinery that is tailor-made to deal with this problem, okay? So it actually doesn't make sense for us to spend too much time doing all this in detail if you're not using the right machinery.
Instead, okay, physical states do not have the A0 dagger, but we're still imposing these the linear mu equals 0 as an operator statement on your physical state.
You're going to see on what we're going to impose that state. Okay. Yes. Okay. Very good. So let's continue. Now we go back to this, and we're going to go back, and we're going to discuss now the way people usually discuss these operators. Did you guys discuss tetrads when you were doing GR? No. Okay, so the following comment will make, will have no meaning, but at some point you will see tetrads, and then you will say, oh, wow, yeah, the deal vines, yes. Fear vines.
We need fear of vines?
We need somebody. We need somebody who's from Germany to tell us how to pronounce it.
You know I'm not disgraced.
Before we get, can you say what you mean by
why not the first and the middle?
These are all our states, right?
Oh, you're saying they can't be created by A0 dagger. Okay.
That's right. This is amusing, actually.
Freddy, can you Lorentz transform for just an observer will have a token A0 dagger, which is a mixture of amounts A0, or how does that?
This is amusing. I lost one page. Is anybody seeing a page? It's not here. And the funny thing is that I saw it before. Oh, it's at the end. What do you know? Okay. So here, standard, and it's actually going to be very useful. So it's not just. So people like to introduce something called polarization vectors. Basically, the idea is that you want to be able to describe polarizations of your field in a way that is independent of the creation and annihilation operators, okay? So you want to separate both spaces, okay? And when you want to separate two spaces, you can introduce, once again, you will see this in a beer vine or a tetrad, okay? And what this means is the following. We're going to introduce a basis of 4 vectors, which we're going to call epsilon mu lambda. Now, lambda can take 4 values because we have a basis. We have to generate the whole 4-dimensional vector space. And of course, this is our regular vector index. Okay. Now, the condition that they generate the whole vector space is that 2 conditions. One,
you have 2 index components that so how are they? How is this a vector?
It's 4
That's the vector index, but what is the lambda?
well,
It's 4
imagine you have R3, right?
Yeah.
And I tell you, I mean, the reason you're confused is that whenever I tell you that I give you a basis of R3, I usually tell you, well, I have vector E1, E2, and E3, right? But imagine that each vector, I don't want to write it with an arrow. I want to put the component in there, right? So you would say, oh, this is very unfortunate. This 1, 2, 3 is precisely in the place where I would like to put the component. So why not putting it up? Now I have a space. So I remove this, and I put the I here. Okay? So I have 4 guys, 0, 1, 2, 3. And this is the vector index. Okay? Okay. Then the conditions are the following. Just take the inner product of these vectors. Okay? Well, this is basically a normalization condition too, but we impose this normalization condition and this leads to a completeness relation, to the following complete which is that if you take all the states, okay, all our base elements in the bases, and you sum over all products of them, you should get back the identity in your vector space. But our vector space is a Lorentzian space, so we should get the metric. Okay? This is actually going to be very important for us at some point.
Can you repeat the motivation behind producing these vectors?
Oh, let's see how we use them, and then you will see why. Okay? So here is what we're going to do. So we're going to expand our operators, okay, in terms of our tetrads, or in terms of our polarization vectors, we should call them.
So should that lambda be down?
Which index?
The lambda be down on either of the systems?
It's convention.
Okay, since you, okay.
Yeah, but let's just keep it there. It's just an index.
Okay.
Okay. So we're defining new annihilation and creation operators that now live in the internal space of possible polarizations. Okay. They are now decoupled from the vector space, from the tangent space of our space-time. Okay. And that's the reason we're doing it, because we want to decouple our creation and annihilation operators from the structure of space-time, from the tangent space of space-time. Okay. Very good.
Are you able to maintain manifest Lorentz invariance by when you do this?
Yes, definitely. This is an internal space now. This is the one that carries the Lorentz transformation. Yes.
So there's something that's starting from here we have 4 sets of operators, right? That create 4 particles. So in this case, you're trading one to create 4 types of polarization, but
yes.
for the same particle, or
they are now mixed, right? This operator is this operator. Okay. So in fact, in the quantum theory, if you now plug this into the canonical commutation relations, you will find the following for these operators. Okay. Okay, and the others are 0. And our condition on physical states will be that we will not consider operators generated by this guy. Okay, so we will not consider operators of this form, and we will see why. Let's get some intuition from the classical theory. So let's go back to the classical theory. Okay, in the classical theory, when we impose this condition, okay, this is now a condition that has to imply something in momentum space this condition implies that k mu epsilon mu lambda has to be 0. Okay? Out of the 4 possible components or the 4 possible polarization vectors that we have to impose that this object vanishes. Okay? That this vanishes. Now, this condition by itself is a single condition. So it tells us that there are 3 polarizations left. So people like to think about the 3-dimensional momentum space.
How are there 3 polarizations left?
Well, we have 4 independent ones, right? And there is one constraint that tells you there is something that has to be, these guys have to satisfy this equation, okay? So one of them has to go. Okay, out of the possible values that they could take as a 4-vector, yes.
Right, isn't that 4 equations?
Yeah.
Like, what's the index lambda doing?
The index lambda is telling you that you have to choose your epsilons such that this is true. So you can choose 3 of them, right? 4 of them have to span your 4-dimensional vector space, right? Now 3 of them, I mean, one of them, I mean, this will define a 1-dimensional space. Okay, so it's telling you that you're chopping off from your space a 1-dimensional space. Okay, so let's actually see how this happens. So in momentum space, you can draw the 3 component of your momentum k. Okay, and you can draw the space transverse to it. Okay, and let's say that you have some vector E1 transferred to it and some vector E2 transverse to it. So what choices can you make for this? Well, you can make the following choices. You can say, well, E mu, say lambda 1, say one of the polarizations, I could choose this vector to be the vector 0, and I could choose it to be the vector E1 and 0 in the last component, okay? And now choosing a basis where this guy is along the z direction, okay, say. And this is in the x and y direction, E1 and E2. So I can choose epsilon mu2 to have 0, E2, 0. Okay? Well, the reason these guys satisfy this condition is that with the choice I made, so I made the choice that k is a vector of the form 0, 0, kz. And with this choice, and remember that k squared is equal to 0, we know that k is now a vector that has the form plus minus k, 0, 0, k. Okay? Now, if you dot this with this, you get 0. If you dot this with this, you get 0. So this two-dimensional space is still a full dimensional space. And you have a third one, a third possibility, which is to choose this guy to be literally that component over here, say. Yes?
So E1 hat and E2 hat are two components.
Sorry. You can choose this guy to be plus minus 1. Sorry?
So E1 hat and E2
yes,
hat.
they are two component vectors
Okay.
that live in this two-dimensional plane. Yes, thank you. So this is a two-dimensional plane. It's an R2 inside R3, which is chosen to be orthogonal to this direction, which now by convenience, I'm choosing to be the z direction. So these guys are the x and the y axis in momentum space. And these are two vectors, any two vectors there, okay? Shouldn't?
These are two component vectors, so it's 1, 0, and 0.
Okay, so let me actually tell you what examples of what these guys are. So some choices. You can choose E1 to be 1, 0, and E2 to be 0, 1. In this case, your 4 vector E1 would be the vector 0, 1, 0, 0. Is that clear now? And in this case, your vector E2 would be 0, 0, 1, 0. So if you make this choice, this is what people call a linearly polarized object, if you only have this polarization vector. Okay? But there are better choices in the sense that they are nicer in order to describe physical systems. So another choice that is...
So any orthogonal, any normalized mutually independent vectors would do that.
Yes. So let me make this choice. Oh, this is terrible. There is an I in there. Well, that's, according to Andres, it's a problem. Why is the I a problem? Actually, that's a good question.
So it seems from here like K is something that is real.
Yes.
So understanding in the emission to this.
Yeah, this is what is called. This is what is called a generalization.
So here, then I have to choose whether. Oh, okay.
No, you're right. This doesn't follow. These guys don't belong to this space. That's definitely true. These guys don't belong to that, to this R2. Yeah, but this is actually a possible choice. And there is no problem with the reality of our object because for A star, we will get epsilon star, okay?
The condition is still satisfied.
Yeah, the condition is still satisfied.
But then you still have to modify your normalization to take into account the star of epsilon.
Excellent. Yeah, that's right. So I better be careful and put a star here. Very good, yes.
In the middle word, why do you have a freedom in plus or minus k? Or n plus?
Because I'm taking k to be future directed or minus directed. But you're right. from our definition, we only have positive frequencies. So we only choose it to be plus. So in this case, this guy would be plus. And we can choose epsilon 0, the last guy, to be, say, something like 1, 0, 0, 0. You say, oh, but that doesn't satisfy this requirement. Well, that's precisely why it's projected out. That's why I didn't write it in the beginning, right? I told you that this condition kills one of the 4, and this is the one that it kills, or at least a representative of the one that it kills. So I can choose this one to be the one that is killed, these other guys to be objects that respect this. But this still contradicts the statement that you all know very well, which is that the electromagnetic field, or an electromagnetic wave, is only supposed to have 2 physical polarizations. So what's the problem? This guy is actually the problem.
2 physical polarizations?
Yes. Have you ever heard that statement that they are supposed? Well, if you haven't, remember from our, well, it's a funny way to actually remember it, but go to our quantum field theory 0 review, right? And look at how many states a particle, a massless particle of helicity plus 1 can have. How many?
2.
Nope.
3, 4.
No. No. No.
X
So,
belonging to the set of
no.
1.
Exactly. 1. A particle, massless particle of helicity plus 1 has only 1 degree of freedom. But we always consider theories that are parity invariant. So theories where, well, at least for the gauge field, at least the theories we know, they must have this fancy symmetry which we haven't discussed, which hopefully they will discuss, or maybe not, which is called the CPT symmetry, okay? And that, well, we also said that in quantum field theory 0. We said that every time you have a particle of helicity plus 1, okay, you must also have a particle of helicity minus 1. So together, they make 2 degrees of freedom, okay? Now, those 2 degrees of freedom are the ones we're trying to describe with this object. But somehow we're not succeeding because we're getting 3 degrees of freedom. We're getting 3 possible polarizations. And we have to get rid of one of them, okay? Now, what's the one that we can get rid of? Well, we started with this guy, but this is a gauge fixing condition that wasn't complete. So we're paying the price of not having completely fixed the gauge freedom. Yes?
I'm calculating wrong, but the epsilon 3 satisfies the normalization condition. I mean, that dot product that you have there is intended to be a Minkowski dot product, or the usual?
That condition? Yes, yes. It's supposed to be a Minkowski metric. Yes.
Lambda equals 3 and lambda equals 3. Then you enter Spanish instead of being at 3, 3. Instead of being that?
If you take the, yeah, that's right. That guy is a null vector. Yes. Well, this is a normalization. I didn't tell you that I made the choice that precisely satisfies as a normalization. You'll have to come up with another choice.
So, I mean, that can be an argument to say, okay, I got rid of this guy. And
No. This is a normalization condition for my basis. It cannot do anything physical to you, right? I mean, it's just a convenient choice of normalization, right? Right, you cannot do anything. No, but there is a better reason to get rid of this, right? We said that the gauge choice was not complete, right? In fact, our solutions do the following. In momentum space, they have this delta function in them. Right? That's the fancy way of writing that measure. In fact, that's the one that I prefer, but just to keep with what we did in week 1, we usually write it like that. And then there is a plus, okay, fine. There is everything in here. So that means that the objects we're describing in momentum space, they contain this delta function, right? So what does it mean? Well, it means the following, that if in momentum space now, imagine the object in momentum space. This object has this delta function, and imagine you choose the wrong polarization, if there is such a thing. You say, no, let me try to construct something physical with this object and see what it is. Well, that guy is here, right? Now, this was with the choice that I made here, right? But this polarization could have been chosen to be just proportional to k, to the 4 vector. Right? Here I chose it to be proportional to the 4 vector in that way because I made the choice that this guy was this. Okay? But epsilon 3 could actually be defined to be proportional to the full 4 vector. Okay? That's how I made the choice here. Right? I chose these two guys, and then I made the third choice to be something that was proportional to that polarization. So I make the choice, so my object now looks like this. Yes. The hat is what people usually use, or maybe people use tilde. Maybe tilde is more appropriate, or hat. Now I don't remember. In any case, so this is the structure of the gauge field when we only excite or we only have that polarization. Okay. So let's see what this is.
So this is the Fourier transform of the field, right?
Yes, that's the Fourier transform of the field.
So
in other words, the inside of this object, basically.
Inside of?
I mean, everything that is in here.
So are we leaving that part out, the big bracket?
Yes, there are more pieces. I'm just saying that this is proportional to this. Yes.
Why do we have the plus on the?
Because we're looking for future directed.
Well, because only when this is plus, we get back that formula over there.
The state.
Right? Remember, we need that. Otherwise, we get two solutions for the delta function, and we're only summing over one. Okay. So that formula is the same as this formula, and this plus was the same as okay. That's the definition. Okay. So when we have this, we say, so what could this possibly be? Right? Well, I claim the following. This thing is nothing but, in coordinate space, is nothing but the derivative is a total gauge. Of course, it has to be a total gauge because we know that we're imposing this condition, which is equivalent to this. But moreover, is one of the guys that we haven't fixed. Okay? I claim that this object here is precisely one that satisfies us this equal to 0. Okay? Can you see why that is true? Well, you see, if I multiply with k, and I put a k here, right? There is this delta function. This delta function tells you that k squared is equal to 0. And therefore, we're going to find that this guy in this polarization is precisely the remaining gauge choice that we didn't fix. Okay? So this is something that we had to expect. We didn't make a complete gauge fixing, and therefore we are left with some leftover polarization. So what do we do? Well, what we're going to do,
That part again, how this implies, I don't know.
well, it's just that there is a delta square. So what I'm saying is that this guy precisely has the form, first of all, is of a gauge form, right? I mean, that's obviously true. But moreover, this function satisfies this equation, which is an extra condition on this W. But this is precisely the condition that we had from the beginning that told us that we couldn't gauge fix completely this object. Okay? It was precisely the leftover redundancy that the condition was not going to fix. Okay? So what do we do? Well, what we do, or what people do in these cases, is that when they consider an S-matrix element or an scattering of these objects, not that we can do it because we still don't have an interacting theory, but if we were able to do it, and you have the scattering, and you say, well, let me say that I'm scattering a particle with some polarization vector epsilon mu lambda, and some other particles. Maybe electrons, which we still haven't discussed, but we should. Okay? And this guy is producing some other photon, some other gauge boson with some other polarization. Okay? So what we should do is that we should impose that every time we ask for the probability of scattering physical data, physical objects, then the probability for producing something that is called longitudinal is actually 0. Okay? So we have to impose that physical requirement. Okay. So the conclusion of the whole discussion is that we're going to be dealing with, so let's actually summarize what's going to happen with our theory. The conclusion is that our Maxwell theory, in order to study Maxwell theory, we're going to promote this to an operator constructed in the following form. Actually, let me see. Yeah, so we can sum our sorry, yes. Just copying what I had up when it was wrong. And remembering that these guys can be complex, we're going to have this e to the I k dot x, okay? So the full operator actually can have it from 0 to 3, but when we think about initial states, we're only going to allow states that are physical. But at the end of the calculation, we have to check that we do not have any probability of producing unphysical states, okay? So we have this, and what else? Well, now that we have this, we have the quantization conditions that we mentioned before on the operators. Yes, thank you. Missing a lambda from the lambda star. So we have the quantization condition on the lambdas, on the creation and annihilation operators with lambdas. And then we can ask what happens what happens to this object, okay? But this should actually be very easy to calculate because so far we haven't said anything about what these guys are other than the fact that they behave like scalar fields, a collection of scalar fields. In fact, if you use the previous description, which I erased, which I shouldn't have, it's even easier to compute what this thing is. Okay? Because now it's literally a collection of n of 4 scalar fields, of 4 Klein-Gordon fields, right? So if you have a collection of 4 Klein-Gordon fields, the only thing that this object could be is literally the generalization of the Feynman propagator when you have several different fields that have different indices. Okay? In other words, it should vanish whenever the indexes are not the same. So our Feynman propagator for the theory has no other choice but to be a copy of the propagator for the scalar field okay? Yes, sorry, I mean D4K. Times sorry, no minus I, it's just minus this. Okay? So this is the only modification that tells us when the two objects can actually produce a state and annihilate the state, and so on. Okay? So we're going to give a name to this object. Well, not a name, but a graphical representation. So we have many different possibilities. And if we had scalar fields with many different indices, we would do exactly the same thing. So we can just say that we have at x a mu, an index mu, and at y, at the point y, we have an index nu. And we have some momentum flowing through this. Okay? So that's how we can denote, well, this would be in coordinate space. In momentum space, we will represent this with a mu, this with a nu, and there will be a momentum k. Okay? So this is a coordinate version, the momentum space version. Okay? But you have the right to complain because there is no use in having a propagator if you don't have any interactions. Right? So our theory so far is trivial. There is nothing to do. Yes?
One thing. So this is just like a collection for scalar fields, and we show that there are 4 sets of creation and annihilation operators. Where does this intuition of the electromagnetic field give rise to photons, which is just one particle, right? But I'm seeing here that
which is one particle that has 2 degrees of freedom. I mean, don't. I mean, the photon is not. If you specify the helicity, then it's a single state. Okay? In fact, so the reason people like to introduce these polarizations is that a photon, as you're saying, a photon with this polarization vector is called a state with a given helicity. It's a state with plus 1 helicity. And this one will be a state with minus 1 helicity. Okay?
So I'm trying to make the analogy what we did in the homework when I have a 2 scalar field space.
Yes.
And we interpret both as particle and anti-particle.
Yes.
Why in that case I don't have the same the same picture here that I have the same particle with different degrees of freedom?
Why don't you have? Well, because these are different objects. This is a real field, but it's a vector field. Okay. It's a vector field. The vector field has 4 degrees of freedom, but that's not what we want. That doesn't describe Maxwell's theory. Maxwell's theory should have only 2 degrees of freedom. So we get rid of the 2 degrees of freedom, and the leftover ones are the physical polarizations, which are the transfer polarizations. In the next course, you're going to use a heavy machinery to actually give a nice way of getting rid of these unphysical polarizations. We're doing literally what we can do if we hadn't discovered anything else, okay? But it works, actually. So we can go very far constructing objects that don't generate unphysical degrees of freedom in the end, okay? By just following a little bit of intuition and then checking that the answers actually do the physical, satisfy the physical property, that every time you ask for something like this to be produced, your theory will give you 0, okay?
So we went through the discussion as to how there are some polarization vectors that are redundant.
Yes.
So why do we still write the field in terms of the 4 polarizations? Why can't we just write it down in terms of 2 that are orthogonal to K and say that that's the description?
Well, you see, we cannot, we didn't make a choice. We cannot make a choice from the beginning, right? We didn't start with Maxwell theory from the beginning. Remember, we didn't quantize Maxwell, okay? So this is a relic of the fact that we didn't quantize Maxwell from the beginning.
We're not quantizing.
No, from the beginning, we didn't quantize Maxwell. And still we haven't. We just said that we're going to follow a set of rules that would allow us to compute things. And in the next course, you will actually quantize the theory formally, okay?
So if this is not quantization of Maxwell theory, what makes me think that I still have only the 2 degrees of freedom for my field and not any other number?
No, in fact, in the way we're doing it with what I told you, we will have to check every time that this guy is not produced. I mean, otherwise, we would declare victory and be done with it. But it's not, in the way we're going to do it, we'll still have to check every time that we're doing something correct in the end.
By quantizing, you're trying to get as close to Maxwell.
Yeah, that's right. Okay, so let's stop here.